Gravity pulls. That is its nature. Every object with mass attracts every other object. Planets fall toward stars. Stars pull on galaxies. Galaxies tug on clusters. Gravity is relentless, patient, universal. So here is a simple question. If gravity pulls everything together, why didn't the universe collapse? At the moment of the Big Bang, the universe was incredibly dense. Matter and energy were compressed into an extremely small volume. Temperatures were unimaginable. Space itself was tightly curved. Under such conditions, gravity should have been overwhelming. And yet the universe did not immediately collapse back in on itself. Instead, it expanded. And it has continued expanding for more than 13 billion years. Why? To understand this, we have to let go of one common misconception. The Big Bang was not an explosion in space. It was an expansion of space. There was no center from which matter was blasted outward into emptiness. Space itself stretched. Every region expanded away from every other region. In the earliest fractions of a second, something extraordinary happened. The universe expanded at a rate that seems almost impossible. This period is known as cosmic inflation. In less than a trillionth of a second, space expanded exponentially, faster than the speed of light allows objects to move through space. But this was not motion through space. It was the expansion of space itself. Inflation smoothed the universe. It flattened it. It diluted irregularities. It prevented immediate gravitational collapse by stretching space so rapidly that matter was dispersed before it could clump. Without inflation, gravity might have dominated instantly. But inflation raises its own question. Why did it happen? And why did it stop? Physicists believe inflation was driven by a field, sometimes called the inflaton field, that carried enormous energy. As this field decayed, it released energy into particles and radiation, seeding the hot early universe. When inflation ended, gravity began shaping the cosmos in a more familiar way. Matter started clumping. Tiny density fluctuations, slight differences in mass distribution, grew over time. Regions slightly denser than average attracted more matter. Stars formed. Galaxies emerged. Gravity was winning locally. But something else was happening globally. The universe kept expanding. This expansion was not a gentle drift. It had momentum. The initial conditions of the Big Bang gave space an outward push. Gravity worked to slow that expansion. For decades, cosmologists debated whether gravity would eventually halt expansion and reverse it. Would the universe slow down, stop, and collapse in a big crunch? The answer depended on density. If the universe contained enough mass, gravity would overcome expansion. If not, expansion would continue forever. So scientists measured. They studied galaxy distributions, cosmic microwave background radiation, large-scale structure. The result was surprising. The universe appeared close to a critical density, balanced delicately between collapse and eternal expansion. But the story did not end there. In 1998, two independent teams studying distant supernovae made a discovery that shocked the scientific world. The expansion of the universe is not slowing down. It is accelerating. Gravity is not strong enough to stop it. Something else is pushing space apart. This force, whatever it is, has been labeled dark energy. Dark energy is not well understood. It may be a property of space itself. It may be related to vacuum energy predicted by quantum field theory. It may represent new physics entirely. But its effect is clear. On large scales, dark energy overwhelms gravity. While gravity pulls matter together locally, forming galaxies and clusters, dark energy drives expansion on cosmic scales. This balance explains why the universe did not collapse. But it introduces a deeper mystery. Why is the balance so precise? If the expansion rate had been slightly slower in the early universe, gravity could have reversed it. The universe might have collapsed before stars formed. If expansion had been slightly faster, Matter might have spread too thinly for galaxies to form at all. The conditions appear finely tuned. Some physicists call this the flatness problem. Observations show that the geometry of the universe is remarkably flat, not curved strongly inward or outward. Inflation helps explain this flatness. Rapid expansion stretched space so much that any initial curvature became nearly undetectable, much like inflating a balloon makes its surface appear flatter locally. But inflation itself requires specific conditions. Why did those conditions exist? Another question arises from quantum mechanics. Empty space is not truly empty. Quantum fluctuations constantly create and annihilate particle-antiparticle pairs. This vacuum energy should, according to simple calculations, contribute enormously to cosmic expansion. But when physicists calculate vacuum energy using quantum field theory, the predicted value is vastly larger than what we observe for dark energy. The discrepancy is enormous, often cited as the worst theoretical prediction in physics. Something cancels most of the vacuum energy. We do not know what. So the universe did not collapse because expansion, inflation, and dark energy counteracted gravity. But that explanation feels incomplete. It tells us how, not why. There is another way to think about it. The universe may not have been required to avoid collapse. There may be countless universes with different physical constants. Some collapse quickly. Some expand too fast for structure. Some last long enough for complexity. We exist in one that did not collapse. This idea, often associated with the multiverse hypothesis, suggests that fine-tuning may not be special. It may be statistical. But the multiverse remains speculative. We have no direct evidence for other universes. So we return to what we can observe. Gravity is strong, but it weakens with distance. As the universe expands, matter becomes more diluted. The gravitational pull between distant regions decreases. Dark energy, if it is a property of space itself, does not dilute. As space expands, more space exists, and with it, more dark energy. Over time, dark energy becomes dominant. In the far future, galaxies beyond our local group will recede so rapidly that their light will never reach us. The observable universe will shrink to our immediate cosmic neighborhood. The universe will not collapse. It will drift apart. Stars will burn out. New star formation will slow. Black holes will slowly evaporate over unimaginable timescales. Collapse is not our destiny. Expansion is. Unless, of course, our understanding changes. Cosmology is still young. Only a century ago, we did not know the universe was expanding at all. Only a few decades ago, we did not know about dark energy. It is possible that new physics will reshape this narrative. Perhaps dark energy evolves over time. Perhaps gravity behaves differently at enormous scales. Perhaps we misunderstand initial conditions. For now, the best answer is this. The universe did not collapse because its initial expansion was balanced by density, shaped by inflation, and ultimately accelerated by dark energy. Gravity forms structure, but it does not dominate the cosmos as a whole. The universe survives because opposing forces are in tension. Pull and push. Clumping and stretching. At every scale, there is balance. And that balance allowed stars to form. Stars allowed heavy elements to exist. Heavy elements allowed planets. Planets allowed chemistry. Chemistry allowed life. If the universe had collapsed quickly, none of this would have happened. We are here because it did not. The deeper question may not be why the universe avoided collapse. It may be why it lasted long enough for us to ask.